Welcome to the section 11.3 video lecture. I am Dr. Scott Spaniel, your instructor for Math 141 Statistics. And here's another video. So today we're going to talk about inferences about two means independent samples. So this is similar to what we've done so far in chapter 11. It's the process for doing the analysis is going to be pretty similar to what we did in 11.1 with proportions and independent samples. And the type of data is going to be pretty similar to what we did in 11.2 because once again, we're talking about means. So just a reminder that independent samples are when we find random samples, but they're not necessarily related to one another. So we don't pair them up or anything like that, like we did for dependent samples. So let's go ahead and just jump in and talk about this section by looking at some examples. So, and we can talk about the differences and what we're going to use and all that while we are looking at some examples. So, in baseball, the American League allows a designated hitter to bat for the pitcher, although this year they both use the designated hitter, but that doesn't really matter for the problem, who is typically a weak hitter. In the National League, the pitcher must bat. The common belief is that this results in American League teams scoring more runs. In interleague play, when American League teams visit National League teams, the American League pitcher must bat. So if the DH does result in more runs, we would expect the American League teams will score fewer runs when visiting National League parks. To test this claim, a random sample of runs scored by American League teams without their DH is given in the following table, and with their DH in the table on the following page. Okay, so does the designated hitter result in more runs scored at the alpha equals 0.05 level of significance? So I just went ahead and gave you the data I think we need in order to do this problem, although I may have missed one piece of data that I do need from the table in order to do this. But let's start doing the problem, and then we'll look at this. So what we're going to do here is we're dealing with means, so that tells you we probably want to do a t-test. But the problem here is we have two independent samples that we want to use. So what we're going to do is use what's called a two-samp t-test, a two-sample t-test. So we go into the graphing calculator, and we go into the menu under statistics, under stat and tests. You'll see that we have a two-samp t-test. Notice there's also a two-samp z-test. We're not going to use that. Okay, all these ones with z's over here on the far left are when you know the population standard deviation, which we don't know, and very rarely will you know it. So that's why we're going to look at these ones with the t's. So we're going to use a two-samp t-test. Yep, and in fact, I am missing one piece of information that I need from the problem, so let me get that out of the textbook. So notice the things it's asking for are pretty similar to a regular t-test. It wants the mean, it wants the standard deviation, and it wants the sample size for each of the two samples. Okay. So, and you don't need to worry about the pooled check mark at the top of the page. Just leave that unchecked. You could learn about that. That is in our textbook, but we just don't have the time, and you don't really need to know about it right now. So yeah, so I forgot a couple of pieces of information that we do need here, so hopefully I'll be able to find it in the textbook. Okay. Okay, yeah. So the part I did miss was the sample sizes, which each one of these are. Okay, so each one of these has a sample size of 30. So that's what I was missing here. So the sample size for the National League is 30, and the sample size for the American League is also 30. Okay, so there's all the information we need. So let's go ahead and put this in. So X bar for the National League is 4.3. The standard deviation for the National League in the National League bar parts is 2.6 with a sample size of 30. And then for the other one, it's 6.0, 3.5, and 30 as well. And so now we've got our p-values. But you have to make sure, once again, that you're choosing the correct p-value. So if we go back to our notes here, similar to what we did in the first section, we're comparing two different parameters. So the first parameter is going to be, and we're dealing with mu here. So our null hypothesis is that they're going to be equal, that the two means would be equal to each other one. So that would be mu sub the National League is going to equal mu sub the American League. Then our alternative hypothesis is going to be that they're different in whichever way is given. So in this case, to test this claim, a random sample of runs scored by the American League teams without their DH and then with their DH. So we've got the National League is without their DH and the American League is with their DH. So does the designated hitter result in more runs? So this is the one that has the DH, is the AL. So we, in this case, would expect the NL to be less than the AL. Okay, in the NL ballparks, to be less runs than in the AL ballparks. And so this, choosing which way this faces, is going to be a very important part of these problems. So which one of these do you expect to be bigger? And in this case, we expect the AL one to be bigger. So that's going to be this first p-value, which is the less than one. So our p-value for this problem is p equals 0.0187. So the question is that less than alpha? Is that less than 0.05? And yes it is. So therefore, we can reject H naught, and we can conclude that there is sufficient evidence to suggest the DH increase. DH results in more runs. Okay, so that's the idea of that. So what I'd like you all now to do, and once again, I think I'm going to need to give you one more piece of information that I didn't give you here. What I'd like you to do is, in 1 second, once I add in the missing piece of information here, which is the sample size, I'd like you to try these other two problems. So, not these other two, this next one here. So in this case, our sample sizes are actually the same as the previous one. So N sub R and B is 30, and so is alternative. Okay, so go ahead and take a few minutes, pause the video and try this problem. Oh, sorry. And it just occurred to me that I left the wrong video up here. So let's look at this. So here's what I had written for those. And then at the bottom of the screen, you can see the information you need to try this problem. So pause the video and try these problems. Okay, so now that you've had a chance to try this problem, let's go through it together. So a music industry producer wondered whether there's a difference in the length of songs of rhythm and blues songs versus alternative songs. He obtained a random sample of each music category and documented song lengths. The results are in the following table, which instead I gave you the summaries here. Test whether the length of the rhythm and blues songs is different than the length of alternative songs. So, our null hypothesis, as always, is that they're the same. So, mu sub R&B equals mu sub alternative. But in this case, he just wants to know if they're different. So, mu sub R&B is not equal to mu sub alt, right? If we're just trying to figure out if they're different, that's all we'd want to do for those. So now we can go into our calculator and we can do a 2-samp t-test, which is just, once again, the capital letters get you here is a shortcut TSTT. In this case, 2-samp t-test. And we can put in our data. So The mean for R&B was 242.7. The standard deviation was 26.9. And the sample size is 30. For the alternative, it was 238.3, 28.9, and 30 as well. Okay, and you can see we're doing not equal to, so our p-value here is 0.5440 if we round to the fourth decimal place. And that is not less than alpha, so we do not reject H naught. So there is not sufficient evidence to suggest a difference in the length of R&B versus alt songs. Right. So that's the idea there. So that's how you would do this if you're given statistics, like we were given here. In both these cases, we were given statistics. If we're given raw data, this is going to work basically the same, except that we have to put in the raw data and then tell it to look for that data. So if we go ahead and look at this here, ramp metering is a traffic engineering idea that requires cars entering a freeway to stop for a certain period of time before joining the traffic flow. The theory is that ramp metering controls the number of cars on the freeway and the number of cars accessing the freeway, resulting in a freer flow of cars, which ultimately results in faster travel times. To test whether ramp metering is effective in reducing travel times, engineers in Minneapolis, Minnesota conducted an experiment in which a section of freeway had ramp meters installed on the on-ramp. The response variable for the study was speed of the vehicles. A random sample of 15 cars on the highway for a Monday at 6 p.m. with the ramp meters on, and a second random sample of 15 cars on a different Monday at 6 p.m. with the ramp meters off resulted in the following speeds in miles per hour. Are the ramp meters effective in maintaining a higher speed on the freeway? Use alpha equals 0.1 level of significance. Okay? So we want to know if they maintain a higher speed on the freeway. So for our null hypothesis, we'll do mu sub on equals mu sub off. And then in the alternative, we want to know, do the meters result in a higher speed on the freeway? So that would be mu sub on should be greater than mu sub off, right? Because higher speed means it'd be bigger results. And then I've got this data in your node sheet data sets. So here's on and off. And so if we copy that, we can paste that into ClassCalc. And notice you can copy them together. And when you do that, it should put on into X sub 1 and off into Y sub 1. And so now we can do a 2 sample t-test, so TSTT. And we want to do it with data. So now all we have to do is tell it where are our two lists. So they're in X sub 1 and they're in Y sub 1. And so there we go. And so here are our p-values. And so we just want to pick the one that matches our p-value. In this case, our p-value is this first one. This middle one. Because we're doing greater than, so p equals 0.0489. And so is that less than our alpha of 0.1? Yes, it is. So that means we can reject H naught and say there is sufficient evidence to suggest ramp meters result in higher speeds on the freeway. Okay, so that's the idea. So exactly like what we just did, except with the data. So this is a lot like doing what we did in chapter 10 with the data. You're just including two different lists into your problem. Okay, so here's a similar problem like that one. So why don't you guys pause the video and try doing this problem. And then when you hit play, we'll go through it together. Okay, so now that you've had a chance to try this, let's go through it together. So the researchers at the University of Mississippi wanted to determine whether the reaction time of males differed from that of females to a go-no-go stimulus. The researchers randomly selected 20 females and 15 males to participate in the study. The go-no-go stimulus required the students to respond to a particular stimulus and not to respond to other stimuli. The results are as follows. Test whether there is a difference in reaction times of male and females at the alpha equals 0.05 level of significance. Okay, so our null hypothesis is that mu sub female equals mu sub male. And our alternative hypothesis would be we want to know if it differs, so mu sub female does not equal mu sub male. And so you can go into I'm going to get rid of what we just did. I can go into my data sets and go to problem number 2. And I can copy and paste this into ClassCalc. Okay. And then we can tell it to do a 2-sample t-test, a TSTD, and to use data. And we wanted to use data from x sub 1 for the first list and y sub 1 for the second list. And what we get is we get a p-value of, for the not equal one, right, that's the one down here, not equal to 0.5403, which is not less than our alpha. So we do not reject H naught. So we can say there is not sufficient evidence to suggest a difference in reaction times between males and females. Okay. So that's the idea there. So once again, just like all the other sections we've done since 10.1, the setup of the hypothesis testing is basically the same all the time. There's some subtle, small differences, and then you just have to make sure you're using the correct hypothesis test. And one of the great things about ClassCalc is if you pick the right test, it tells you what it needs, okay, in order to run it, what information you need to type in. Okay. Then the last thing in this section, similar to all the sections we've done before, is going to be now let's do the same thing with confidence intervals. So to do the same thing with confidence intervals, we're going to use the 2samp t int, okay, which is hopefully what you would expect, but that's what we're going to look at, so the 2samp t int. So 2 Dutch researchers conducted a study in which 2 groups of students were asked to answer 42 questions from Trivial Pursuit. The students in group 1 were asked to spend 5 minutes thinking about what it would mean to be a professor, while the students in group 2 were asked to think about soccer hooligans. The 200 students in group 1 had a mean score of 23.4 with a standard deviation of 4.1, while the 200 students in group 2 had a mean of 17.9 and a standard deviation of 3.9. Based on the research of de Jurquois, this problem is based on that research, so I'm not going to try to read all those names. Determine the 95% confidence interval for the difference in scores from mu1 minus mu2. Interpret the interval. What does this say about priming? Okay, so the key thing here is to make sure you put in your first group first, because your calculator automatically does first group minus second group. So when we go in here, I'll get rid of what we were doing a second ago, and we can go to stat, test, and grab the 2samp t int, or that should just be TSTI for 2samp t int. Either one gets you there. And notice you can either put in raw data or you can put in the statistics, which is what we have here. So in this case, the mean for sample 1 was 23.4. The standard deviation was 4.1. The sample size was 200. For group 2, the mean was 17.9. The standard deviation is 3.9. The sample size was also 200. And then they want us to do a 95% confidence interval, so 0.95. Okay, and you'll notice it gives us our confidence interval. And notice, hopefully this matches up with what we did, which is mu1 minus mu2. So our confidence interval here would be 4.71, comma 6.29. Okay. So what does that tell us? Well, it tells us that that there was a difference in the scores, right? It's because 0 is not in the interval. So that means we can conclude that there is a difference between the groups. And so what does that say about priming? Well, it tells us that priming before a test is very important, right? Coming in with the right mental state. So you can take that back to when you're doing your own test. It's important to be thinking about things that get you in the right headspace to do the process you're about to do. Okay. So now you've tried that one together, why don't you guys go ahead and take a moment, read this second problem and give it a try, and then hit pause, and then when you're ready, hit play, and we'll go through it together. So in a Gallup poll conducted August 31st to the September 2nd of 2009, 513 national adults aged 18 or older who consider themselves to be Republicans were asked, of every tax dollar that goes to the federal government in Washington, D.C., how many cents of each dollar would you say are wasted? The mean wasted was found to be 54 cents with a standard deviation of 2.9 cents. The same question was asked of 513 adults aged 18 years or older who consider themselves Democrats. The mean wasted was found to be 41 cents with a standard deviation of 2.6. Construct a 95% confidence interval for the mean difference in government waste of the mu sub r minus mu sub d. So that last part is important because that means we want to put the Republican information in first. So we're going to do 2 sample t int, so TSTI, and we can put in the means. So the mean for Republicans was 54 with a standard deviation of 2.9 and a sample size of 513. The mean for Democrats was 41 with a standard deviation of 2.6 and a standard sample size of 513. And then the confidence level was 95%. And so that gives us a confidence interval of 12.7 to 13.3. And how could we interpret that? Well, we could interpret that as, yes, there is a difference between how much Republicans and Democrats think is wasted because 0 is not in the interval. Okay. So that's it for 11.3. So we've now gone through all the different types of hypothesis tests and confidence intervals that we're going to do for chapter 11. So when you come back, for the next video, what we're going to look at is putting it all together, which is just going to help us make sure we're selecting the correct method for the problem we have. Don't forget to do the homeworks and quizzes and tests. And as always, if you have any questions, feel free to email me or send me a message, and I will get back to you as soon as possible. See you next time.